the agenda for today. So if you can go to the next slide, please. Thank you. So today we'll have an introduction to Save on Energy. We'll review some common HVAC systems found in multi-unit residential buildings, or MURBs. We'll have an overview of heat pump technology, understand sources of energy savings opportunities in MURBs. We'll discuss implications of oversized systems, and then there's going to be a presentation of some case studies. And so with that, I'd like to introduce Vicky Gagnon to walk us through item number 1, an introduction to Save on Energy. Vicky is a business advisor with Save on Energy. She'll start our session by presenting information and updates. Oh, I'm hearing some feedback. Andrew, if you could please turn your microphone off, please. So she'll start our session by presenting information and updates on energy incentives and training programs that are available to support owners and operators of multi-unit housing facilities. Vicky, the floor is yours.
Excellent, thank you. Next slide. So I'm Vicky Gagnon. I work on the retrofit program at the ISO, and the retrofit program supports businesses with capital projects that save electricity. Eligible facilities include commercial buildings, multi-residential buildings, including condos and apartments and affordable housing, as well as institutionals, universities, hospitals, and agricultural facilities, and more. Applications are submitted and managed through the retrofit program portal, which can be accessed through the retrofit page on the Save on Energy website. Last May, the custom track was reintroduced to the program, along with some other updates, including increased incentives. And the $1 million incentive cap was removed.
Oh, please turn your microphone off. Thank you.
But please note that the 50% project cap remains in place. And network lighting controls incentives also moved from a per square foot basis to a kilowatt hour basis. So it's now 35 cents a kilowatt hour. Next slide. In the fall, some additional program updates occurred. The retrofit program's prescriptive incentives increased as of October, and most non-lighting measures have increased a great deal. Majority of the prescriptive non-lighting measures have increased. Some have doubled, tripled, or even quadrupled, including many in the HVAC measures. The Instant Discounts program for lighting launched on December 18th. In this program, incentives are paid directly to distributors, enabling them to offer instant point-of-sale discounts on energy-efficient lighting to customers. And as a result of this new program, incentives for most lighting are no longer offered in the retrofit program, with the exception of some specialty lighting, like horticulture lighting. Next slide. We wanted to illustrate the significance of the increases. So we have a few examples here. Most air source heat pump incentives have quadrupled to up to $18,000 per unit. Demand control ventilation for enclosed parking garages also have significant incentive increases. Unitary AC incentives have increased significantly, along with the majority of VFD incentives. For example, 150 horsepower VFD was previously eligible for $9,800 and is now eligible to receive an incentive of up to $29,400 per unit. A 5 horsepower VFD was previously eligible for $350 and is now eligible to receive an incentive of $1,050 per unit. And there's a complete list of all prescriptive incentives on the retrofit webpage. Next slide. As part of the local initiatives program, the ISO has introduced retrofit regional adders in some areas of the province where electricity constraints exist. For these targeted areas, all non-lighting prescriptive measures are eligible for double the incentives normally available. And so that includes the new increased incentives as well. So even with those new increases in these areas, the prescriptive non-lighting incentives are double. And the purpose of these increases is to assist in reducing the demand for transmission assets in these constrained areas. So the list on the left had increases available since May. So Niagara, Kingston, Southern Huron, Perth, Pembroke, and Kenora. And in October, the additional regions were added on the right: Wabashing, Barrie, Muskoka, Elmira, and Peterborough, Belleville. And all of the postal codes with eligible target areas are listed on the website. Next slide. The Energy Affordability Program is for income qualified participants, and most social housing providers and their residents may be eligible for this program. It offers 2 levels of support. For more middle income participants, there are energy saving kits, which include light bulbs and clotheslines and weather stripping and shower heads for electric water heating. And for those most in need, there's a comprehensive support, which includes a number of measures available in the kit. And based on the results of an in-home assessment, participants may qualify for Energy Star certified replacements of appliances such as refrigerators, freezers, window air conditioners, or dehumidifiers. And if the home is electrically heated, participants may also be eligible for insulation in their walls, attics, and basement as needed, as well as a comprehensive home draft proofing. Next slide. We know it's important to build and support capability in energy efficiency sector, and we also know that the proper installation and maintenance of measures is key to realizing the desired savings and performance. And we've recently refreshed our suite of course offerings, and we have over 20 courses which are now eligible for incentives. Next slide. Through a collaboration with Enbridge, you can receive up to 75% of training costs on eligible courses. Next slide. And we're expanding our tools and workshops and webinars, as well as coaching, peer learning, and other information resources and guides available on our website. So stay tuned for updates about fully funded capability building initiatives by visiting Save on Energy training and support. And with that, I'll turn it over to start the main webinar.
Thank you so much, Vicky. So with that, I'd like to introduce Dragos to take us through the rest of our efficiency HVAC operations for multi-unit housing sessions. Before Dragos, you begin, please just a reminder to mute your microphone. Make sure that it's muted. We've heard some background noise during Vicky's presentation. It can be disruptive to the presenter. So just make sure it's muted. Thank you.
Thank you, Alice, and thanks everyone for joining us today for this session. I do encourage you to be interactive. We have a relevant number of people here. Hopefully, we can have a dialogue on some of the topics we discuss. And at that time, you can enable your microphone for sure, no problem there. I don't mind if you have questions during the presentation. We have a certain time allocated at the end for this Q&A part of the presentation, but we don't have to wait to clarify a certain aspect or have a comment during the presentation. So as I said, it's an online presentation, but let's try to make it as interactive as possible. If you can share your camera, to be even better. We can make it a bit more interactive in that way as well. But that being said, I'm going to start my technical presentation on the multi-unit residential building opportunities with an introduction to the mechanical systems we see in our buildings, HVAC system we see in our buildings. And the first the first classification we can make would be between centralized and decentralized systems. So I would start with a decentralized system because these are older type of systems we had in our buildings. We had systems designated for each space in our buildings, but these systems were able to provide several functions. So we had integrated devices that were assembled in factory environments for efficiency. We provided heating, cooling, ventilation with these devices. So we had this type of initial design in a decentralized mode. And then for large buildings, multi-residential buildings, high-rise buildings, we came up with other efficient modes. But if we want to remember what we've seen, and actually we can still see in several buildings built in the 60s and 70s, some of these type of equipment, very popular. We see window air conditioners. Buildings that do not have air conditioning as a centralized system offer this type of upgrade to occupants. Through the wall room HVAC systems, that's a type of alternative to the window option. It requires a bit more construction, it's more disruptive to the building envelope. And then if we look at more sophisticated, maybe moving towards more commercial systems, we see single zone variable air volume system, for example, which are serving a certain area of our building. I mentioned that as we wanted our buildings to be more comfortable, more efficient, we switched to a centralized design. So centralized system includes a central component, central plant, chiller plant, for example, or heating plant, and included a number of other additional equipment to provide that technical function for the equipment. As I said, these are in a central location, and then we have to, now the challenge is to distribute this source of energy, the heat and cooling that we have in a centralized location, distribute that throughout the building for a comfortable environment for occupants. Examples are central refrigeration equipment in a chiller plant. We have a chiller, we can have pumps if we use water to distribute the cooling energy around the building. We have cooling towers. So an assembly of equipment items that together operate as a system to provide the cooling required for the building. For heating, we have central plants with boilers, pumps, if we use a hydronic system for distributing this energy throughout the building. In older buildings, we may actually even see steam in some places, although in many cases we convert this energy from the steam to hot water before we actually distribute it in the building. One example that's still used throughout many central plant systems on university campuses or hospitals is with the central steam plant and then distributing the heat inside, let's say in the residence building in a campus, a multi-unit residential building on a campus using hot water after we convert the heat from steam to hot water. So moving back where we started with the decentralized system, initially we were using indirect sources of heat. So we were using direct sources of heat. That was a very efficient option to transfer heat from a fuel, the chemical energy of the fuel, convert it through combustion into heat, and then release that energy in the space. But the downside is that we had to live with combustion products, flue gas that results from burning a certain fossil fuel, and then impacting the indoor air quality of the building. And in majority of the buildings nowadays, that's not an acceptable option. So we switched to an indirect type of heating. And in this case, we need to have a heat exchanger that allows us to convert the heat from those hot flue gases, the gases that result from the combustion of fossil fuel in the boiler, and convert that to the air that we have in the space for comfort. And the indirect system is pretty much what we see in most of our buildings nowadays. Small, large residential buildings use some form of indirect heating to prevent that problem we saw with the indoor air quality. Now, we talked already about, I mentioned already the heat transfer. We need to convert some form of energy, the chemical energy of the fuel, into heat, and then distribute this energy in the building for a comfortable environment for occupants. In this process, just based on basic laws of thermodynamics, we are going to see losses. And it's important to understand how we define the heating efficiency so that we can identify sources for improving this. And this is a chart I found in one of the resources, the literature resources, that shows, maybe the numbers are debatable, but it shows a clear progressing from the total energy available in the fuel that gets through combustion, converting to heat, and that's the burning efficiency that we see on the chart there, which is as much as we can get out of this chemical energy. The problem is sometimes we have incomplete combustion, and that's a little bit of unburned fuel that's left in the flue gas. Manufacturers tend to design this equipment for zero unburned fuel, but through tuning, through operational conditions, there might be some form of fuel left unburned. Anyway, this is a small component. It should be insignificant, less than 1%. And then this is basically the heat that we release from the chemical energy. And we can then look at the path of transferring this heat all the way to our space. But not all this heat, as we work with an indirect heating system, gets to be transferred towards the space. Some of it will be lost. And you see here in the first group of losses, we have sensible heat. This is because in the combustion reaction, we release some molecules of water that, if we don't condense them in a boiler that is not designed to condense the vapors from the flue gas, will be exhausted in the atmosphere and take with them the amount of energy we need, the latent heat of water that will be now present in the vapors. We have in designing these combustion chambers and burners, manufacturers tend to optimize the amount of air that you add to the fuel for the full combustion. So, depending on how many molecules of natural gas you have, we need to provide a certain number of molecules of oxygen to have full combustion. And to be on the safe side, most of manufacturers will design a little bit of excess air. So we want to be, if we are off by a certain margin, we need to be on the safe side. So there will be a little bit of excess air. That unfortunately adds to the inefficiency of the boiler, because with that little excess oxygen, there is a lot more nitrogen from the air that passes to the boiler and then is exhausted. So with this, we get to a level where we call this steady state efficiency. This is what manufacturers like to show us, because this is the efficiency, the maximum efficiency that they can show us in controlled environments. Usually they use this under specific parameters, and they can measure it when the boiler achieves a steady state or any combustion equipment. Unfortunately, in our operation, in our buildings, we can't operate the boiler at steady state. We have on-off cycles where we get to add additional losses to our process. And again, in addition to that, we have the distribution system. And what we actually use in the end, we define as seasonal efficiency. And this is, as you see in this chart here, could be as low as 40%. For high efficiency boilers, that may be around 85% efficiency. So we still see that we get this type of, I guess, opportunity if we address some of the losses here. If we reach to that 85%, there is not much more we can do. So that's where we are going to look into alternative solutions for heating and cooling in our buildings. And one of the topics that we are going to cover will be heat pumps, very trendy now in discussion for retrofits related to heating systems. But let's finish this discussion here on and I've added here the heating seasonal performance factor, which is going to be further discussed in the heat pumps, because this is a way for us to define the efficiency of the heat pump. We can't really call it efficiency, and I'll explain why, but this is basically accounting for the useful output, basically the BTUs of heating that we provide to the building for each watt-hour of electricity input into our equipment, into our heat pump. So first of all, you see is not even using the same units of measurement. And that's coming from how we defined efficiency in the cooling systems for quite a long time now. Very common to see this in literature. Manufacturers, again, used various indicators. We used the energy efficiency ratio, popular with many equipment manufacturers because it's easy to replicate the numbers in control conditions. But what we are interested in from our perspective of users is the seasonal energy efficiency ratio. And as you see, the formulas are fairly similar. One is though showing this over a longer period of time, over a season, and it's again defined based on certain methods, standards, and protocols to be able to compare equipment from various manufacturers. And this is what we see in, let's say, Energy Star equipment, the equivalent of the seasonal energy efficiency ratio. But as you notice in the formula, the units of measurement are funny. I mean, we use the denominator expressed in units of energy or units of power for ER, BTU per hour, using the imperial system, and we use in the denominator watt-hour as a more popular unit for electricity, because the input in the heat pump is electricity, the output heat is expressed in different units. So to avoid confusion, some manufacturers just completely forget about showing the units and they just show you a number. So ER 22 or ER 15, that's what we see on the equipment, or SEER, as a matter of fact. But we know that behind that there is actually a unit, and it's a different unit for the numerator versus the denominator. For larger equipment, or if you want to avoid this confusion with the units of measurement, we are referring to a coefficient performance, which expresses both the numerator and the denominator in the fraction here in the formula using the same units of measurement. So the logic here is that I'm looking at the output. What is the useful output from this equipment? Basically, the energy that I use for heating and cooling, and in the input power would be the power, the electricity that we supply to the motor that drives this equipment. And again, we can define the COP for heating. We can define the COP for cooling as well for our heat pumps. So we can basically complete our discussion on equipment unless we also discuss about the heat transfer. We said that in the indirect heating mode, which is the majority of solutions are based on indirect heating mode, we use some form of heat transfer. And you see that this heat transfer happens in 3 modes: conduction, convection, and radiation. Most of our equipment will have a combination of these 3 modes. Now, what we are interested in is enhancing by designing these heat transfer, heat exchangers, by designing or enhancing one of these modes. And based on which one we focused on, sometime manufacturers will refer to those heat exchangers as radiators or convectors, to highlight what form of heat transfer is preponderant. But all of them will have some form of a combination of those heat exchangers. Now, I have a few pictures. You may have seen them around your buildings, other buildings in the industry. Older buildings may see these large heat exchangers. which are cast metal, cast iron, and they provide certain heat transfer function, but they are not very efficient in transferring the heat from the fluid that flows through these tubes to the air in the space. We've also seen alternative to this where the heat exchanger has an improved heat transfer feature because we now have we have a flow of air that drives over the heat exchanger. So behind this case, we may see a fan that drives the air around the heat exchanger. Various examples, moving on to further improving the efficiency of this heat exchanger. Over time, we design heat exchangers in materials that are better options than the cast iron. We have heat exchangers made of copper with fins to increase the heat transfer area. Aluminum is another option for this type of heat exchangers we see in our buildings. And as I mentioned, always by adding a fan, as we see here, we just remove the cover from this picture. By adding a fan, we improve the heat transfer because now we have more volume of air passing over the coil and therefore absorbing more heat from the fluid that passes through the tubes of this coil. Or other forms of design, unit heaters, which are, again, a choice that we've seen storage areas, garage, parking areas, sometimes loading docks, not necessarily in spaces occupied by tenants in multi-residential buildings. If we look at how we transfer heat inside the units, we have options based on when we require heating or when we require cooling. Very popular in multi-residential buildings that have individual unit control for the heat delivered to the space. We have two pipe systems. And in that case, the changeover happens in the central plant location. We switch from cooling to heating based on the period of the year. In many cases, we have regulations that ask building operators to provide heating at a certain time of the year. And inside the unit, we just control how much heat we take over from this central system from the distribution loop and distribute it in the space. And in this case, we use a fan to distribute the heat in the space. In a more sophisticated system, we may see 4-pipe connections. So in this case, we basically have the option for the unit to decide, do we need cooling or do we need heating? Again, assuming that the central plant operates both for chilled water and for hot water. So this type of system is usually more efficient in shoulder months when maybe the units facing south would require cooling and the units facing north may require heating if the temperature is appropriate for that. So with a 2-pipe system, once you decide what you provide, you would only be able to provide heating and cooling, and each unit will just be able to control how much of it they use. With a 4-pipe system, you get the full flexibility, but there is the significant additional cost to be able to distribute both forms of energy, heating with a hot water loop and cooling with a chilled water loop. Inside the unit, I mentioned the fan coil there. Just as an example, we have heat exchangers that will take this energy from the hot water loop or for the chilled water loop. We have fans that typically drive this energy through the air and distribute it into the space. And similarly, as we decided before with a 2-pipe versus 4-pipe, we have two options here as well in designing our fan coils inside the unit with 2 coils, one for heating, one for cooling, or a combined coil, a common coil but then we have to use a system of valves to decide and select, are you using cooling or are you using heating? So in this case, we have a valve that will connect the return to the cold water system if you are in cooling mode, and another valve that will connect to the supply cold water system, but also modulate as much as we need this flow of water here, all controlled by a thermostat in the system. So two-pipe system seems to be the most frequent one. If you have the four-pipe system, we can have a two-coil or the common coil as a system. Very rare we are going to see the two-coil in multi-residential buildings. This is more of a specific application where we need to have cooling and heating pretty much at the same time. So hospitals, museums, maybe. So that being said, we got to the point where we see what we mean by heat pumps. So all that conventional equipment we decided to investigate in our building based on central plants, chiller equipment, boiler plant equipment, and where would the heat pump fall into place here? So first of all, let's first understand what the heat pump is, because that will allow us to see how we represent the efficiency of the heat pump. And this schematic here is showing very simplified schematic, shows that in a heat pump, we have four components. We have the condenser and the evaporator. These are two heat exchangers, show like a coil. And we have a compressor and an expansion valve. So this, if we think about this separated through a vertical line, what we have on the compressor side, so on the right side of the schematic between the two heat exchangers would be in gas form, and what we have on the right side would be in liquid form. And with the compressor, we are now increasing the pressure. So if we draw now a horizontal line between the expansion valve and the compressor, anything we have above the line would be low pressure, and anything we have below the line would be high pressure. So we control the pressure here, and this will allow us to condense the refrigerant that flows through this pipe system, to condense the refrigerant at a temperature where the condenser will reject the heat, and then will evaporate the refrigerant in the evaporator by absorbing heat from where we want this heat to come from. So we basically have a source of heat where the evaporator absorbs the heat, and then we have a sink where the condenser dumps this heat too. Now, if we use this in cooling mode, which is how we use this type of equipment, we call it vapor compressor cycle equipment. In cooling mode, the evaporator is going to be the coil we have in our space. We are going to absorb heat from the air in our conditioned space, and we are going to reject heat through the condenser outside. So that's how we've done, air conditioning since the 50s, 60s in our residential buildings. But now, if we reverse the cycle, we can use this heat pump equipment to collect heat from outside. So if the heat exchanger that's outside now will evaporate the refrigerant at a lower temperature, we absorb heat from the outside there, and then we discharge this heat in the space in the house through the condenser at a much lower pressure. So higher pressure is going to allow this refrigerant to evaporate even at low temperature, and will release this at lower pressure in the space. Now, the efficiency of this vapor compression cycle operating in cooling mode in Canada is impacted by the fact that we have such a large temperature difference. If you think about a heat pump that operates at negative 16 degrees, we had that these days, the temperature outside. So negative 16 degrees, and let's assume we have 20 degrees inside, 20 degrees Celsius set point for our space. We have a delta T of 36 degrees that this vapor compression cycle needs to fight. So basically take heat from the negative 16 and push it into the house at positive 20 degrees Celsius. So 36 degree delta T, where in the summertime, even if we assume the worst case scenario, let's say 35 degrees Celsius outside temperature, we take heat from the space at, let's say 22 degrees, not 20, as we keep the set point in the winter, 22 degrees for the summer. And we push this heat outside at 35 degrees Celsius. So the delta T is only 13 degrees Celsius. So that makes the work of the vapor compression cycle, compressor work less during the summer for the same amount of heat that we need to transfer. So we'll see that in some of the studies that we used as a reference for the presentation here. So basically, a heat pump has two modes. We use them in heating mode or in cooling mode, depending on the season. However, because our climate here is so cold, sometimes when we remove heat from cold air, we can actually get to the point where the moisture in the air is going to freeze. And that requires the pump to get into a defrost cycle. Nothing different than what we see in our refrigerator. Smart refrigerators nowadays know when the coil is covered in ice, and then they switch to a defrost cycle, basically reverting the coil, reverting the pressure, and now rejecting heat into the coil that's frozen to melt the ice. And that's how a heat pump operates as well. So that's a function of the conditions, the weather conditions, the content of moisture in the air, the temperature. So all this is part of the analysis, and I'll show you the impact on the efficiency of the pump in a couple of slides. Now, I mentioned air source heat pumps because these seem to be how the industry is evolving very quickly now. We have a lot more research done to make these heat pumps efficient at low temperatures. There are heat pumps that are designed to operate reasonable at negative 25 degrees Celsius, which is covering pretty much all year heating season in our climate zone. But we also have an option to use ground source heat pumps. Multi-unit residential buildings may see this as an option because we are using now the ground. I mean, the cost to install the heat exchanger in the ground is higher, but we can easier include one of these options when we look at centralized systems. So in the ground source heat pump, this is nothing new. I mean, we've seen installations based on ground source heat pumps since the 80s in Canada as a response to a push towards energy efficiency. And some of these installations are not operating efficiently because the problem with the ground is that we need to have clear understanding of the capacity of the heat exchangers that's underground. So we need to have studies done. We need to see how much energy we can remove from the ground before it needs to be replenished. Because in our climate, we use a lot more energy for heating. So we remove more heat from the ground than we put back into the ground from cooling during the summer. So just to show how the two modes operate, this diagram here shows the reversion that happens in the flow. They are basically valves that automatically switch the direction of the refrigerant flow, and the two heat exchangers exchange roles. So in heating mode, we have the condenser inside. That's where we dump the heat. So this is our sink, and then outdoor would be our source. So this is the evaporator outside. And then the two reverse roles in cooling mode. I mean, this is something that we see more frequently now. Maybe a few years ago, we would have assumed that this is just a split system for air conditioning. We see how it looks in an installation in a multi-unit residential building. It has one of the two heat exchangers with a compressor outside, and it has the second heat exchanger inside. So again, the two heat exchangers exchange roles in heating and cooling mode. This here will then distribute the air inside the space. It has a small ventilator here that circulates the air for good convection transmission to the heat in the space. Now, I mentioned that temperature is very important for this, because the temperature, I mean, set points for spaces are usually within a certain small margin, but outdoor temperature changes tremendously in our climate. We go from -16, as we've seen yesterday, even lower than that. And we go all the way up to +35. So we have a large range of temperatures, and therefore we see the efficiency of the heat pump impacted by that temperature. So for that reason, there were studies done on see what exactly it means for efficiency. And as you see here, an example for a unit that we've seen part of one of these studies. It has an indoor unit that distributes the heat in the space. It has the outdoor unit, and then we calculate the heating efficiency. I will call it efficiency in brackets because, as you see, it's more than one. We call this parameter that allows us to compare different equipment. And we see that is 9.4. So the useful heat that we can get for 1 unit of electricity input into the motor that drives the compressor is 9.3 as a multiplier. In cooling mode, we can get 14 units of cooling out of 1 unit of electricity that we put into the motor. So I just mentioned that in the summer we see less delta T. That's reflected in these two parameters. Capacity-wise, we also impact a bit the capacity of the heat exchanger with the temperatures. We can also take advantage in the heating mode from the heat of compression. So the electricity that we put in the compressor is now useful. So for that reason, sometimes you see a little bit higher capacity in heating as an example here. But what I wanted to point out is the efficiency that we can see here. So when we are looking at cooling, the lower the temperature, the better, because that means we have less work to be done by the compressor. And we can see this here. So for that reason, most of the time, the SEER in our climate is actually a better number than the EER, the energy efficiency ratio, because we have those shoulder months when the equipment actually operates better than the equipment operated, the equipment tested in defined conditions by manufacturers. But when we get to heating mode, things get changed pretty quickly. So in heating mode, and that's the darker color curve here, the coefficient of performance drops quite fast. So for -16, a temperature that we can see, maybe not many days, but we can still see in heating mode, the coefficient of performance is only 1.8. So that means that we can only take about 2 units of energy from outside, plus the electricity we put in the motor, to deliver in the space. So if the electricity in the motor is the denominator 1, we basically take only 0.8 units of energy from outside. So 1 unit is from the motor, 0.8 from the outside, then we get a coefficient of performance of 1.8 for our heat pump in those really cold conditions. But still better than, if you remember the efficiency of the heating system based on combustion devices, fuel combustion devices, we had only 40 to 85%, depending on the efficiency of that system. So we compare 85% with 1.8, which is equivalent to, say, 180%. I will call it again efficiency in quotes because, again, we can't really have efficiency over 1. We can see now that manufacturers are really good in designing their systems. Capacity is fairly steady over the time. The equipment is actually able to provide the sufficient heating for the space. It's just that it's not reaching that beautiful efficiency of 4, 5, even 3 COP of 3. Just as a source of information, if you want to do a quick high-level assumption for your systems, Redscreen Expert software package offers some guidance on taking these numbers in a reasonable range. So for heat pump systems, 130 to 200%, because is going to be the equivalent of the efficiency, but that means 1.3 to 2 COP as a seasonal system. High efficiency condensing boilers up to 85%, as we've seen before as well. So that's what we see in heating mode. For cooling systems, again, we have various technologies we use here. COP during the summer for cooling would be higher. Typical nowadays, we look at 4 or 5, depending on what type of a system, even higher than that for really high energy efficiency systems. So keeping in mind that there are periods when we actually have rather low energy efficiency, it's not a lot of time when we get negative 15 or even lower, but we do have those period of time. We still need to provide a source of heat. We need to provide the heating for maintaining our buildings in a comfortable range. We can definitely look at how to control that. But before we get there, since we covered pretty much all equipment, I'd like to use an application we have here. It's a Mentimeter. So I have a poll that I'm going to share with you. And I would like you to vote. The first one that we have here as a question is, just select which of these systems are present in your buildings. Centralized or decentralized? First vote came in pretty quick. Good. And I've already seen, we see this ratio about it's almost 10 to 1, which is no surprise. Like a majority of the buildings, especially if we look at rather large buildings, will be based on centralized systems. This was the design that was more efficient, more effective, both technically and economically. So no surprise here. So thanks for sharing your input here. Now I have a second one here. Let's move on to the next one, which is just to understand how the refrigerator uses this heat pump mode. So what do you think when we talk about the refrigerator? Is that in heating mode or in cooling mode? I see the first answer coming in quickly. And I see majority picking the cooling mode. So I guess, democratically, we have to accept that as being the correct answer. But also technically, that is the correct answer. Because if you think about the purpose of the refrigeration cycle, the vapor compression cycle for the refrigerator is to remove heat from the inside where we want to keep our food at a lower temperature and dump that heat outside. So we operate that as a heat pump. We basically get heat out of the refrigerator, we dump it into the building. So if we use the refrigerator for preserving our food, it is a heat pump. Now, if we use the refrigerator for heating our house, which is not the way we actually use the refrigerator, that will be in heating mode. So in the cooling mode, which is how we use the refrigerator to keep our food preserved, is basically how that device was designed. But from the house perspective, that is a heating mode, because I heat the pump with that energy that I dump from the refrigerator. Okay, good. So let's return to our presentation. And I mentioned that, we don't need, to invest always. I mean, if we can, perfect, but we don't need to invest in high efficiency, like heat pump systems for the entire load of our system. If we think that our system is going to operate for a limited number of hours in that perspective. So what we actually look for is to try to optimize how we use our resources by having in the base load whatever is running the most time, the most efficient equipment, and then stacking up equipment that's less efficient, but it's costing less. It's easier to maintain. It lasts longer, maybe. And it does use more energy, but is using that energy for a low amount of time during the year. So that's where we can use this cascade control. So we try to prioritize.
Oh, Dragus, seems you muted yourself. Can't hear you anymore.
Thank you, Alice. And I'm not sure how it happened, but just let me know as soon as it happens.
Of course, we just lost a few seconds.
Okay, perfect. So, what I was inferring to is that we try to prioritize the systems so that we run the most time, the ones that are more efficient, and then we stack up systems that are less efficient, but they are not meant to run as long as possible. So that's an example here of optimizing based on efficiency. So with this, I guess we can wrap up a discussion about what we see in our buildings, and we can move on to identify opportunities. Now, I talked mostly about the HVAC systems, but funny thing, when I'm going to start looking at opportunities, the first building system that I'm going to refer to is the building envelope. And that's something that the industry is starting to realize in Canada. At this climate, with our climate zone here, we need to look at the building envelope for energy efficiency. So building envelope is the system that preserves our heat inside. So basically, we know that we can never completely stop the heat transfer. Heat, according to the principle of thermodynamics, heat will flow from high temperature to low temperature. But we can slow down this transfer. And that's what we are trying to do with the building envelope. We design building envelope that will control this heat loss or heat gain during the summer. We can also gain heat through the building envelope to our best comfort in the space. Now, the heat will still be lost from the building, no matter how good the building envelope it is. So we are going to have some cooling systems or heating systems to compensate for that. But at least with the building envelope, we try to prevent that. So if we look at a schematic that shows this type of heat transfer that happens through the building envelope, we have solar heat gain, direct radiation that either penetrates through the transparent components of our building glass or is absorbed by the opaque components of our building envelope. We have conduction that happens when the heat, when the air temperature is higher outside than it is inside. So we'll see this conduction happening as well. We have infiltration that will be present in our buildings. This is basically because we have different temperature, different pressure from inside the building versus outside, either due to wind or due to unbalanced HVAC systems. So this is heat exchange with the exterior, and then we have inside the space heat that we need to address. So we have sources of heat, internal loads, could be people, could be appliance, equipment in the building. We also know that our buildings need ventilation, fresh air. So we have exhaust air to allow for that fresh air to come in. So we do have to deal with a fairly complex problem here. To improve the efficiency, we have to basically use this heat transfer, all those modes that I mentioned, in a proper way. So what I'm looking for is two elements. We are looking at the thermal resistance and the shape of the building, but once the building existing, so we can't really change that amount of surface that we expose. So thermal resistance of our building envelope. We are also looking at the air leakage that we have in our buildings. So thermal resistance of building envelope and air leakage are what we are looking for here. So for the thermal resistance here, the insulation of our buildings, we see a diagram on the right side of this slide. What we have inside our wall structure is material that will operate as a brake, as a resistance in the path of heat that tends to travel from high temperature to low temperature. So from during the heating system from inside the house towards the outside. So we want to prevent this here. When we have uninsulated world types like the ones here, in addition to this, we have radiation that happens in this space. So for example, we may have glazing that is showing this type of heat transfer as well. So increasing the performance of the building envelope addresses both the glazing component as well as the opaque component of the building envelope. And we see minimum requires for our buildings increasing. More difficult to do this for existing buildings. In terms of improving the R value, requires additional layers on the building envelope. So if you look at where these weaknesses are in our building envelope, we have thermal bridges that are created by the structural elements in our buildings. Steel, aluminum components, concrete are structural components of our buildings that create these thermal bridges. We may have the geometry of the building with balconies, different shapes of the buildings that increase this exposure of the structural elements to the outside, and therefore presenting an opportunity for the heat to flow freely through these thermal bridges. Roof protrusions, different penetrations we have for mechanical systems can increase this heat transfer as well. So in high-rise buildings, especially, we also see the need for these vertical paths for the air, staircases, elevator shafts, mechanical shafts we see in our buildings as well. So these vertical shafts act as a chimney and therefore creating a draft. Easier to understand this in the example here. So creating a draft because warm air is lighter and rises, therefore creating negative pressure at the bottom of the stack. And I'm sure we all experience this in tall buildings, elevators. They are fairly noisy in the winter because that air that escapes through the stack. And in some cases, very rare though, but you can see sometimes the elevator's doors do not close because the draft of air passing through creates sufficient pressure so that the protection system is activated, so the doors will not close. We also see this infiltration created by the pressure caused by the wind. So we see higher pressure on the wind side of the building. And in some cases, we may see poorly balanced systems creating this imbalance of the pressure from inside to outside. So if we exhaust more air than we include into the building, introduce with the makeup air units, we unbalance the system as well. And again, I wouldn't say all buildings, but several multi-unit residential buildings, high-rise buildings, will see this type of effect in the corridors. The corridors in multi-unit residential buildings are meant to be pressurized to prevent, exhaust air coming from the units, let's say cooking or bathroom, to come into the corridors. But sometimes you can feel that because the balancing is not operating properly. So what we see in our buildings is a cumulative effect of these three: the stack effect plus the wind plus the unbalanced mechanical systems. So that air is basically introduced at the bottom of the building. It has to be conditioned because now it's in the space, and then gets exhausted at the end at the top of the building, removing with this significant amount of heat or a significant amount of energy that needs to be added back into the building for comfort. So the wind effect, as you see here, increases typically with the height of the building. It's present on higher elevations of the building. And we've seen in some retrofitted buildings, typically from the 60s and 70s, that had issues with the water at the top of the building, had water penetration caused and driven by the wind inside the wall. And the solution that was applied in some of these cases was adding an extra layer of cladding to prevent the water from penetrating in the building. In my opinion, that's a lost opportunity, because at that time could have been also considered an increase in the thermal insulation of the building as well. So whenever we do this type of improve in the building efficiency, in the building envelope efficiency, we would like to address the air tightness. We would like to make the building tighter. And some of the examples we see here are showing the type of retrofits we are doing. So air sealing, increasing the insulation for opaque building envelope, making sure that windows are installed properly with air tightness required. And if possible, we want to verify the success of this retrofit that is aimed to increasing the air tightness with a blower door test or the thermography. And air tightness was addressed in multi-unit residential buildings for a long time. We used to do caulking around the windows, the doors frequently, or not frequently, but periodically. But that's what we are now looking at more efficient building is beyond that, just the caulking. So we are looking at improving the airtightness of the air barrier, adding insulation, um, sealing all the gaps around the windows, doors, any other mechanical openings. And to test the air tightness in our buildings, we use easier would be to use the thermography. So we have infrared cameras, but these typically give us a qualitative aspect of the air tightness. We can really measure the airflow with these air tightness. We can identify weak points. They will show in different colors on the infrared camera. But if we want to actually measure the infiltration rate, we use a blower door test. And for anyone that used that, blower door test is a fairly large piece of equipment. And if you think about a large building, it's actually becoming a fairly complex installation. That's an example of a blower door installed here. It's a multiple of actually blower door. We have 12 fans that pressurize or depressurize the building in order to be able to calculate the airflow. And we do this pressurization or depressurization of the building at various levels of pressure. We typically, in order to be able to compare apples to apples, we report the results at in a format of air changes per hour at 50 Pascal of pressure differential. But 50 Pascal of pressure differential is a very rare condition that the buildings actually see. It typically sees much lower pressure differential. However, if we have the lower pressure differential, we will be able to measure the flow. So the blower door test will give us an airflow that we actually measure and we can compare. So the industry is using this indicator, air changes per hour at 50 Pascal. If we use the thermography, I mentioned that we can see this qualitative result here. Warmer colors, orange, yellow, red, represent higher temperature areas, which are caused by either a thermal bridge, as you see with the balconies. Windows as well represent a weak element in our buildings, because the best window may not have as good as thermal performance as the the worst opaque wall system in our buildings. We also see at the top level the effect of the stack effect or the exhaust air. So the infrared camera is a quick tool that will allow us to identify problematic areas in our buildings. Using these tools can guide us. An infrared camera, a blower door test can guide us to identify and quantify the problem, so that we know that we have an opportunity for improvement. How do we improve that? How do we make the building tighter? Now, we combine that in most buildings that were retrofitted, and we'll show some examples in a few minutes. We combine that with the thermal insulation upgrade. So if we have a chance to increase the R value of our walls, we can also aim for reducing the infiltration rate. For opaque building envelope components, this is the main measure. It is an expensive measure, so it's a capital project that we are talking about here. For transparent components, glazing, that will be windows, some doors, we can look at energy efficiency improvements by using sealed units, insulated glazing units with double glazed as a minimum. And as we look at now requirements for new construction, we kind of need to move on towards the triple glazed windows. If you go to trade shows or look at the catalogs from manufacturers, there are windows out there even with 7 layers of glazing. Now, the purpose of these layers of glazing is that we want to improve the R value of the glass, of the window, And the glass is not a very good insulator. What we care for is the gap of air or other gases that we have captured there. That's why we have those insulated glazing units that will give us the higher R value. And for having multiple layers is because at low temperatures in our climate zone, we would create convection inside the window. So the air or whatever gas we have will start to transfer heat from one pane, the cold pane will get heat from the warm pane if we create this convection current inside. To prevent the convection current from increasing, we have to make the gap smaller. So on one side, we want more gas between the panes, so we want a bigger gap. But on the other side, to prevent convection, we want a smaller gap. So the only way to do that is to have multiple layers. And that's why we see triple glazed panes, because now we have 2 gaps of air, or quadruple panes, we have 3 gaps of air. But we can't really enlarge the gap of air, which means that, typically you have to buy the window that's designed for that particular climate zone. So, windows for warmer climate zone will perform very poorly in cold climate zones. Moving on to air sealing, I mentioned that it's part of the comprehensive upgrade. In thermal insulation upgrade, we add the improvement in the air barrier, but we can also continue to do what we've done before for air sealing, caulking, weather stripping for some of the mobile components, operable windows, doors. These are measures that we've done in our buildings, and we can continue to do that. Again, we refer to thermal bridges as being now important, significant for our buildings as we improve the R value of the opaque components. Having these structural elements exposed and acting as a thermal bridge is important. So, for example, building codes now require continuous insulation layers in our buildings that will prevent the thermal bridge effect. So, with this in mind, I'd like to share another slide with Menti. And we finish this one, so we can move on. Can move on to this one. So this is a kind of an open answer. You just type your suggestion here. Can you think of factors that can drive air leakage in buildings? Open windows, yeah, definitely. They create the gap that, the stack effect will take advantage. Some balconies may add to the complexity of, those are all those penetrations for plumbing, mechanical systems. And true, someone mentioned freeze-thaw cycles. I've seen this happening in some buildings where the vapors that pass through the building envelope cause this issue. So it's very important to account for that as well. Yeah. Excellent questions. Sorry, excellent answers. So staying on the same line, I have another open question here. Why is ventilation important for multi-family units? We don't want to completely seal the building. We've done this in the 80s, unfortunately, without doing the research, and we created that sick building syndrome that caused many problems. So we don't want to get there.
But yes,
air quality, pretty much, yes. And various, there you go. So now we actually know a lot more after these 3 years of research done as a follow-up of problems the buildings had and concerns building occupants had for indoor air quality. So we've done a lot more on this. And we do need this ventilation because it's a one way to prevent the impact of various elements in our building, including viruses and bacteria that can be replicated. Okay, very good. So with these, I guess we can move back to the presentation, and we'll talk about another opportunity we have, especially in existing buildings, when we consider energy management project, energy efficiency improvement projects in our buildings. And this is related to oversized equipment. We do get more losses because some of the losses are a function of the capacity of the system, some of the losses are a function of the load. But for the losses that are a function of the capacity of the system, we are going to lose this amount of energy no matter what the loads are. So it's kind of a standby type of losses. And I'm sure everyone may have seen this type of stories in the past. We've seen buildings where the designers select a certain size equipment, and they look into the catalog and they pick the next available size, the next available up size, because more is better. Then the contractors take the design drawings and they look for equipment that will meet the requirements. Let's say the capacity specified is not available, they will look at an alternative and get the next size up. So by the time we get to use the building, we end up with significantly oversized equipment. I've seen many reports done in existing buildings where the chiller plant is operated at 60% capacity in the warmest day of the year. What does this mean? It means that that chiller is actually having 40% capacity that's not utilized, and maybe in that very warm day, it's not a big deal. It's actually good to have a little bit of spare capacity, but for many of the other days when we don't need that much cooling, the chiller is going to operate less efficiently, and sometimes even creating problems for servicing the chiller because of that capacity. So cycling this on and off can cause the problems, and it is due to the higher capacity than required. So whenever we are looking for this energy efficiency, we have the chance to actually right size the equipment for the next project, and definitely it's much easier to do that when there is a capital project in plan already. Exhaust ventilation in units, we do need to provide the fresh air, as we discussed before. And if we put fresh air in that building, we need to remove air from the building. We have to maintain the building pressurization. In multi-unit residential buildings, we have bathroom exhaust, we have kitchen exhaust, we have dryers exhaust in some installations where the units have the laundry equipment. So the balance of this is very important, and having exhaust leaving the space means that we are removing also energy. That air that we remove for the exhaust is already conditioned to the space requirements, and bringing fresh air to replace it will need the conditioning as well. So this exhaust, if it's not well balanced, will cause that negative pressure to drive the infiltration. But even if it's controlled, so we balance the amount of makeup air we bring to compensate for the exhaust, we still need to condition that air. Areas where we want to control this are usually kept under slightly negative pressure, so that if we have exhaust air, it's going to pull air from other spaces. For example, bathrooms will pull air from the living areas to replace it after it's exhaust. So traditionally, or a conventional type of design, we supply air to ventilate buildings in common areas. We do that through the corridors. We pressurize the corridors to prevent air coming from the units in the corridor. And then we also compensate for the air that is exhausted. So this, in a design environment will look perfectly fine. And sometimes in operation, we see problems there because it's not balanced, and still air coming from the units will be pulled into a slightly negative environment in the corridor caused by, let's say, the stack effect. But in the way we design it, as presented in the diagram on this slide here, we supply air in the corridors, and that air will be exhausted through units. Units have a slight opening under the doors to allow this airflow to penetrate from the corridors. Now, as we move towards more efficient buildings, so newer, tighter buildings would require some form of ventilation dedicated to each unit. So we can really rely on this system that was pushing air in the corridors to pressurize and then push air under the door to compensate for the air that was eliminated by the exhaust fans in the units. So what we are looking basically is to provide this type of dedicated outside air that decouples, to provide this type of air in each unit separately. So we have dedicated outside air systems in which the only function for this would be to provide the fresh air in the space. So it's 100% fresh air. We may condition that. We heat it and cool it, or humidify or dehumidify. We filter it so that it meets the requirements for the space, but it's dedicated outside there. So this outside there is meant to compensate for the exhaust air that we remove from the building. Very seldom we are going to use this for space conditioning as a distribution system for the heating and cooling. So how we do this in an efficient way? We basically use heat recovery. So heat recovery is going to remove heat or transfer heat from one flow of air to another. So fresh air flow passes through a heat exchanger, crosses with the exhaust air, and whatever direction, whatever flow is at a higher temperature is going to absorb energy from the other flow. So this type of devices, heat exchangers that remove heat from the exhaust air during the winter, or bring heat from the space in the summer, we can see them achieving somewhere between 75 and 95% efficiency, depending on the type of heat exchanger. So we see this solution for improving efficiency for the dedicated air, for the outside air that we provide to the building. Now, in units, in multi-unit residential buildings, we are going to see other easy to implement upgrades. We can use timers for devices that would otherwise waste energy by running longer than required. Timers for kitchen exhaust fans or bathroom exhaust fans. We can use thermostats. Smart thermostats are very popular in our buildings nowadays. We can not only have the convenience of many functions that the thermostats do, but they come with a logic that can improve the efficiency in the building. We can use upgrades in the lighting system. Although by now, I guess the technology is so popular that it supports itself. It doesn't need a business case for LED upgrades. The quality of the light is there. The reliability of the lighting fixture is there, despite sometimes having, a failure. It's something that can support a lighting retrofit by itself, especially in multi-residential buildings. We have common areas that have lights on for almost 24/7, like a long period of time. We have upgrades for efficient appliances, laundry equipment, dishwashers, stoves, refrigerators. Energy Star rating equipment is kind of the norm in the industry here. But we also have easy measures to implement that are related to operating and maintaining the building. And especially because most of this highly efficient equipment to use, HVAC equipment to use, requires more care, requires to actually maintain them as specified by the equipment manufacturer. So if we were considering an atmospheric boilers 20, 30 years ago, that boiler may run now continuously without any maintenance. But if we have a high efficiency boiler and we do not replace the air filters, we are basically setting that boiler up for failure, because the heat exchanger will fail due to the impure air, or if the filter restricts the airflow into the device. The type of operating strategies that we can also consider, definitely look at the design, using proper modeling tools to right size the equipment, selecting the option that will look at the operating aspect, not just the first cost. Cascade control, I mentioned that is a way to prioritize which equipment will run more based on the equipment efficiency. As equipment becomes more more efficient, it does require that retuning, recommissioning periodically, and we'll see this as part of our buildings as well. Increasing the air tightness, so basically reducing the infiltration rate. We can continue to do the caulking, the weather stripping on a regular basis as part of operations. Once in a while, I wouldn't say it's a norm yet, but I've seen more buildings. Once in a while, we can use technology to help us identify problems. Thermography is applicable to any building. Blower door test, easier to apply it for smaller buildings, more complex for larger buildings. And then we can add heat recovery to our ventilation. Parking garages are another example of systems where we can use the heat recovery. So that being said, we are at the end of our presentation. So what I have left is a few slides with examples of projects we can very quickly go through. It took me a little longer, so I hope you will have time, if you have questions, maybe to discuss them. That's an example of an air source heat pump system in a multi-residential buildings, low-rise multi-residential building. And because we had electric heating before, this is an economic, it has a reasonable business case to support it as well. So not only the energy efficiency, but also we see some savings on bills. So looking at this here, you can see that we addressed more of a deep retrofit in this building here, beyond just one system. We looked at domestic hot water as well. So looking at, and I wouldn't say it's applicable to all projects, but just to have an idea of this example here, we achieved 29% reduction in the heating energy. We've seen 56% reduction in domestic hot water energy by using heat pump technology there, and improving the efficiency of water use, low flow fixtures. There was an additional 30% of water consumption. I'll jump to the next example here, which is an example of a high-rise building. This is a 13-story multi-residential building in Vancouver. This had the building envelope project implemented, upgrade on the window side, improving the air tightness, re-enveloping the building, increasing the R value from R4 to R16. We've added measures in the parking garage, and improving the control of the makeup air unit in the system, in the building as well. Looking at some of the findings, what was shared by that project. We see what the recommendation is for ASHRAE 62.1 in terms of ventilation, so fresh air provided to the space. We see that as we move up, we had more than required, so that presented an opportunity for improving efficiency because that air is not required. But you also notice that we had the problem with the lower floors where we did not provide the amount of fresh air required for this in this case. So we had most buildings either under ventilated or over ventilated. So it was an opportunity for this project to correct the problem. And that's where the stack effect basically impacts the building air distribution. So findings here, we looked at the problem with air coming from the space, so the pressurization of the corridor wasn't operating properly. And then I'll jump to another project under the tower renewal program. This is a multi-unit residential building in Hamilton, Ontario. It achieved a very high level of improvement in efficiency. It's a high-rise building, 18 stories, but it requires significant investment in this project. So if you look at the results, the findings here, so we've done triple glazed windows. We improved the R value of the building envelope. So the idea here was achieve as much as we can on the building envelope side because it's an existing building. We have limitations on what can be done. So opaque building envelope improvements. So R38, we have glazing, triple glazed, and we also achieved a fairly low, as a matter of fact, measured here as being 0.23 air changes per hour of 50 Pascal. This is tremendously low. So in terms of building envelope, and then we used air source heat pumps in addition to this. But again, the loads are much smaller because we dealt with the building envelope first. So as a matter of results, we've seen 89% reduction in the thermal energy demand intensity. This is an indicator that's very popular with this high efficiency performance. So we are looking at the energy, the total energy that's associated with the demand, with the heating of the building. So that was reduced by 89%. We reduced the greenhouse gas emissions by 88% in this building. And again, it's a combination of improving the building envelope, therefore reducing the loads, but also because we switched to heat pumps, this project switched to heat pumps, and we are using electricity now for driving those compressors. Just as some of the metrics for this last project I presented here. So I had 250 kilowatt hours per square meter in the initial intensity, and we are dropping that. We've seen this reduced to 22.3 kilowatt hours per square meter in this building. And air changes per hour, again, we reduced from 5 to 0.2 in this building here. As a matter of fact, 0.2 allowed this building to achieve something which is not, again, mainstream in our industry, but hopefully is going to at least allow us to learn some lessons from this type of buildings, the passive house certification. So using passive systems will allow us to improve the performance here. Just to look at some of the modeling that was done, can see here modeling for the installation of the windows to reduce the thermal bridges that are created in the building here. We've done this 2D modeling to prove that we do provide that insulation level required. So with this last example of a building, I'd like to open the floor for questions, comments, and as I mentioned, I hope you'll have a few minutes to stay on the call for this.
How long do you think we have, Dragus?
I would say just in
2-3
interest
questions.
of time, let's say 12 minutes. So
All right. So if you have a question, please share it in the chat, or maybe you can raise your hand and ask it yourself. Dragos, I'm not a presenter right now, so I don't think I'll have the option to see who's raising their hand.
no, there were a few good comments in the chat. I see them there. I hope you'll have a chance to check that. I won't read them again, but there were a few comments there as well.
There is one, but we're missing the context. Maybe Earl wants to open his mic to explain. You ask, is it the industry standard to have these deep cleaned every year? And what is the cost of this maintenance? I'm not sure which part of the presentation this is specifically about. And maybe Earl wants to unmute and let us know. If not, if you can ask question directly in the chat again. We did go a little over the time that was prepared. So, and I see that we're losing some participants. So maybe I'm just gonna thank everyone for joining us today. Just so you know, the recording and the slides will be sent to you via email in the next few days. If you have questions, you can reach out to this email address, which I'm sharing in the chat. And thank you again for joining us today. Thank you, Dragos.